So then we move on to like standard operators, okay? So like any programming language, you can add, subtract, multiply, divide, and so on. All right, so here we just have a quick demonstration of all the different, standard operators that you can implement in Python. So second mini quiz is, can anyone tell me the difference between division and floor division? So don't be shy. Okay, so even just looking at this operation, so we have division 4 divided by 2, and then we have floor division 4 divided by 2. All right, can anyone see the difference between the outputs of these two? Yeah, okay, so that's your first hint. Okay, so you can see that the first case, I've divided 2 integers and I got a floating point value in return. And in this case, I've divided 2 integers and got an integer in return. So let's see what happens if we change the values. Okay, so if we wanted to divide 3 by 2, which is a little bit a different case, we can well, we should update this as well so we can see clearly. So obviously 3 divided by 2 is 1.5. 4 division of 3 by 2 is 1, right? Because 1.5 is a floating point value, right? You can't have an integer fraction. So essentially you get the nearest integer in your floating point, which rounded down. Okay, so this is an important, again, but subtle detail to notice, right? That if you're doing a floor division, you're really expecting an integer value at the end, and you should understand when you're dividing these values what you expect to get out of that, right? Because if you just do a standard division, you will get a floating point value. And if you want it to be an integer, you're going to have to convert it. If you do a floor division, you will get a floating point value. And if you expect an integer, if you expect a floating point, you'll have to convert it. So these are important, like, subtle details, but you should be aware if you see some division, or if you're implementing a function yourself, that you know that which type of division you want to perform on your data set. Okay. Any questions about these operators? It's pretty basic. Okay. Okay, so then we have our logic operations. So I haven't put all of them. I just put the the very basic ones. So we have our true and false booleans, and then we have and or operations that we can perform on them, right? So of course, true and true always gives true. True and false gives false. True or true gives true, and true or false gives true. So does everybody understand this logic? And everybody comfortable with this syntax? Okay. So quiet room today. Okay. So then we'll move on. Okay. So functions, right? So this basic Python syntax for function is the special command def, where so in short for definition. So we're defining the name of our function, open brackets, right? So this can be left open if empty if there are no arguments to the function, or we can pass an argument. Colon, don't ever forget your colon, and then whatever your function is supposed to do. So in this case, it's just a simple print statement. This one has no argument, this one has an argument, right? So we can see in the first case, we evaluate the function, and in the second case, we pass the argument 5 to our function and evaluate it. Right? Everybody happy with that? Perfect. Okay, so now if you're familiar with all of those topics, we can move on to something a bit more Pythonic, what's called the lambda function. Okay, so I just showed you the standard syntax for defining a function, right? So we had a def statement and the name of our function, brackets, colon, and then the evaluation. Right, so for the lambda function, it's going to be slightly different. So let's take an example first, just doing it in the standard way, and then we're going to evaluate the same thing using a lambda function. So we're going to just find a function that squares an input value. So we're going to define a function that it takes an argument and returns the square of that argument. Okay, so of course, if we stick in 3, we should get 9, and we do. Okay, so the lambda version of the same thing looks like this. Okay, so you can already notice that it's quite different. So firstly, in the previous So in this example, I didn't have to do any evaluation, right? So basically, the def function is defining my object, which is the name of my function, right? So that I can call this function directly after. In this case, I'm doing an assignment, right? So basically, I'm taking a random variable, which I'm just calling the name of my function. And then I'm assigning to that variable the lambda function, right? So basically, lambda is a special command in Python that tells you that you're creating a lambda function, which is a shorthand for a generic function. It works exactly the same way, but the syntax is just slightly different. So it's exactly the same function that we saw before, but in this case, what we're doing is, okay, here, after the lambda, I'm passing the arguments that are going to go to my function. So x, colon, exactly the same as in the previous one, and then what my function evaluates, which was the squaring of the value. Okay, so you can see here that basically what we have here is very similar to what we had with the previous case. We have this special thing, lambda, but the most importantly is that we have to do an assignment, right? Because there's no object created by this in itself. So we have to assign it to an object, hence the equals. Okay, so then we can evaluate that in exactly the same way. Any questions? Yeah. Well, it's shorter, right? So basically, I can write a whole function in one line rather than what was like 3 lines before, right? So you can have a much more compact way of defining very simple functions. I would recommend, no, you can actually have extreme amount of complexity in a lambda function, but I would recommend only using it for simple things. So we'll get on to when you should use it in just a second, but I just want to explain, make sure everyone understands how to use it. Yes. Yeah, so I mean, well, you could, but you have to be pretty clever, right? So it is possible to do really complex things, like I said, but it's not as trivial, and it becomes very hard for the user to read, right? So the thing is, like this case, this lambda function is extremely explicit, right? Because it's argument and evaluation, single variable, extremely simple. There's no question. Everybody who can read this understands what it's doing. Right. So in the next case, we just have an example with 2 arguments, right? Where we could say, okay, I'm defining a lambda function that does an addition. I have 2 arguments and then my evaluation, right? So very simple, very easy. Now I have here written a caveat specifically for this point, is that it's important in Python to understand how lambda functions work, but you should use them sparingly. And the reason for this is that the main difference that I would argue between a standard function and normal function is that in a standard function, you can add documentation, right? So you can have a doc string where you explicitly explain what the inputs are, what the outputs are, what you expect to happen, what the equation that you're evaluating. You can have a very rich amount of documentation explaining everything that that function is supposed to do. Whereas the lambda one is just one line explicit, right? So if it's not readable in itself, then it's probably not a good lambda function, right? So this is, again, this is, your own intuition should dictate when you should use it or not. But like in general, if you think that it's not understandable on its own, then it probably should just be a standard function with documentation. If it is that explicit that you're just saying, okay, this is just squaring a value, I don't really need to write a function with documentation explaining how to square a value, then it's probably fine. So, I mean, I leave that to your own discretion, but it's just important to understand how it works so that if you see it in somebody else's code, you understand what it's doing. Okay. Any questions about lambda functions? Great. Well, I guess we're going well. Okay, so now we're going on to unpacking. So unpacking is something that is extremely Pythonic, and it might be a little bit hard for people who are coming from a different language to get used to. But once you get used to it, you'll find it hard to go back, let's say. Okay, so when we looked at that very simple example of indexing a list and a tuple and the immutability and immutability, we showed that if we wanted to look up a value from a list, we write a square bracket and an integer value for the index position that we want. right? So in this example, if we have a tuple with the values 1, 2, 3, and I want to look up the second value of the tuple, I would write the name of my tuple, square brackets, and the index that I want, which is the second index, and that gives me my value. That should be pretty straightforward for almost anyone coming from any language. The syntax might be slightly different, but the idea is almost exactly the same. You start indexing from 0 all the way to the size of the array that you're dealing with. Okay, so that's all fine, but Python offers a really nice way of unpacking this information in a more compact and user-friendly way. So imagine if I wanted to unpack all of the values from my tuple into individual objects. So let's say I had a tuple with 3 values, and I want to have 3 independent objects that are assigned to each one of the values from that tuple, right? So one thing you could do is you could say, okay, value 1 is equal to my tuple square brackets 0. Value 2 is equal to my tuple square brackets 1. Value 3 is equal to my tuple square brackets 2, and unpack it that way, right? But that's extremely tedious. So imagine if you had 1,000 values to do like that, you know, it's going to be really ugly and so on. Now, I can't imagine a situation where you would need to do that, but just, you know, you can think about it that way. So one of the nice things that Python does is automatic unpacking. So if I say, rather than assign a single value to an object, I could say I have 3 objects and I do an assignment to the whole tuple. What it will do is automatically unpack all 3 values into all 3 objects. So if you can see here, this one line, I can now print out the 3 values, and I've unpacked all 3 elements from that tuple, right, automatically. So is that clear? Does that everyone understood what just happened? Okay, so that's cool. But what if I had 3 values in my tuple and I tried to unpack it into 2 objects, right? So now I have a mismatch between the number of values in my array and the number of objects that I'm trying to create. Okay, so here I'm going to try 2 values and my 3 element tuple, and you can see it raises an error because this literally tells you that there are too many values to unpack, right? So I'm trying to unpack 3 values into 2 objects. It doesn't make sense. Well, Python has a way of dealing with this, and it's something that you will probably use or see in other people's code and maybe never think about or understand what's going on, but today you will. So there's a special operator in Python, which is the asterisk. So we saw it earlier when we were talking about the basic mathematical operators for multiplication, right? So most cases when you see an asterisk, it's going to be a multiplication. In Python, it has a second use, and it's used as what's called a positional expansion operator or a splat operator sometimes. And what that does is basically has kind of like magic unpacking features built into Python. So I'm just going to show you some of those features and show you how to use them. So firstly, we're going to reprint that same tuple that we had before, the 1, 2, 3. And then I'm going to print the same tuple, but now with this splat operator in front of it. And what you're going to see is in the first case, I print out the full tuple as a single object, right? So what I've evaluated is, what is my object? My object is a single thing, which is an array of 3 elements. In the second case, I've unpacked the values. So you can see now that there's no bracket there, right? So it's the individual values from that tuple. So they've been unpacked from their casing. So you can imagine like taking a box of biscuits or something and just pouring them out. Okay? Clear? Okay. So how can we use this? Well, imagine we go back to that example where we're trying to unpack 3 values into 2 objects. Well, in the first try, it didn't work because it told us there were too many values to unpack. So now what we're going to do is say, okay, I want you to unpack these 3 values into 2 objects, but one of these objects, I'm putting the splat operator in front of. And what you're going to see is that what that does is says, okay, so the first object, I want one specific value for, and then the second object, because it has a splat operator, is flexible. So basically anything that's left over, you can stick into me. So what it does is it unpacks the first value, 1, into the first object, and then the remaining values from the tuple, 2 and 3, get created, put into a list and assigned to that second object. Is that clear? Okay. So basically, yeah, what this is doing is just kind of saying, I have some flexibility here. And that way I don't need to know how many elements there are in this array. Basically, the first one wants one element, and then anything that's left over is mine. Okay, so now we have a little puzzle. Right, we have a list. Yep. You can convert the object afterwards. Yeah, so basically, because what's happened, here is an unpacking and packing step, right? So basically, we've unpacked the tuple, and then we've packed the remaining elements of the tuple into a list. So yeah, the default for packing is a list, but you could convert this object. So I could probably say tuple star val, and then it will probably create a tuple of that object rather than a list. I mean, but you can always do a type on your object afterwards just to make sure you know what you've packed into. Okay, so here's a little puzzle. So now that you understand perfectly what the splat operator is doing, so let's say we have a list of 5 elements, and we're going to unpack those 5 elements into 3 objects, right? So we have val1, val2, and val3, and we've added the splat operator in front of val2. So can anyone brave raise their hand and tell me what values will be assigned to val2? Okay, so I saw Valeria's hand go up. Is anybody else feeling brave? No? Okay, yeah, go ahead. Yeah, so 282, you're saying? Correct. Right, so that's exactly right. So essentially what's happened here is the first value is looking for something at the beginning, the last value is looking for something at the end, and then it says, okay, we'll pack everything that's left in between those 2 points into me, which is a list of 3 elements. So that's exactly right. So I think you've got it. Everybody else understood? Okay, so right, so now you got an idea of how this unpacking works. So I mean, it's hard to think of a concrete example where you might use this in your own work, but you might have some case where you need to unpack things of unknown size, and having this extra splat operator gives you that flexibility. So I'm going to give you a more concrete example of how this can be used in a slightly different way. I've got one more little quiz for you. Okay. So this one is a nested unpacking. All right. So rather than having just a list or tuple of elements, now I have a list of tuples, each of which contains 3 elements. Okay. So we're going to do a double unpacking step. So firstly, we're going to unpack the list, and then we're going to unpack one of the tuples. And what I want somebody to do is tell me what the value of B should be in this example. Any guesses? Yeah. Okay. 6 is correct. Okay, so let me explain just in case you weren't able to catch it. Okay, so what's happened? So in the first one, we're unpacking the 3 tuples. So we have A and B. So B is expecting something at the end, and A is getting everything else. So B is going to be the tuple 7, 8, 9, and then A will be a list of the tuples 1, 2, 3, and 4, 5, 6. Right? So then in the second step, we're going to unpack the second element of A, right? So which will be the tuple 4, 5, 6. Right? And we're going to unpack that into 2 things. And again, B is looking for the last thing. So that will be the last element of that tuple, which is 6. Clear? Right. So that's a little bit tricky, but it's just to give you an idea. I mean, again, not many cases where you're going to be doing something like this, but being able to understand how that recursive unpacking works is pretty helpful. Okay. Well done, Virginia. Okay. So now let's go to something a bit more concrete. So this is where you're probably going to start using this unpacking in a more practical sense. And that's in context of functions. Okay, so here's an example, right? So let's say we have a function that takes 3 arguments, a, b, c. In this case, it evaluates a plus b minus c. Doesn't matter what it does, but we can clearly see that we would expect 3 values to be input into the function, and then we get a single value return. Okay, so imagine instead of just calling the function and sticking the 3 values in, somebody had given me a tuple of values that they want me to put into the function, right? So the boring, let's say, non-Pythonic way would be to say, okay, I have my values, and then I would call the function my values bracket 0, my values bracket 1, comma my values bracket 2, right? So it would be really ugly, long evaluation to just unpack those 3 values into the function in order to get a single thing. Well, we know that we can unpack all of those things in one go with this splat operator. So we can simply call the function, pass the tuple, and then tell it to unpack the tuple values into the function, and it works, right? So now you can start to see how, this might actually be beneficial, right? I have, if I know that my tuple going in has the right number of elements that's needed for this function, then I can unpack them directly into the function and get the evaluation I need without having to do some intermediate step and really ugly explicit indexing of the list element. So that should be pretty clear from what we just covered, right? So nothing different happening here. We've simply unpacked inside the function rather than doing 2 separate steps. Okay, so now let's look at something a bit different. Now, instead of taking an object and passing it to the function, unpacking it, let's tell the function to unpack itself. All right, so how does this work? So basically, imagine you have a function and you don't know how many arguments you want it to have, right? So rather than saying ABC, maybe this function is going to have 100 arguments at some point. I don't know. Right now, I have 2 arguments, but maybe I'll add a 3rd one. Maybe I'll add a 4th one. So rather than explicitly writing A, B, C, D, and so on, I could say, okay, I want you to take arguments, however many arguments you're going to pass, and unpack them. All right, so then I end up with a list object, which I can calculate the length of, right? So essentially, I could write a function that counts how many arguments have been passed to the function. So I can call this function, I can pass 3 arguments to the function, and it will tell me that it received 3 arguments, right? So then if I add another argument, I get 4 arguments. And in fact, it doesn't even matter what the types are. I mean, I could make this one a float, and I could make this one a string, and there's still 4 arguments. It doesn't care what the arguments are. It's simply counting how many arguments have been passed in this particular example. So you can see now this is starting to become really useful, right? Because in many cases that you're going to have some flexibility to your function, right? You might be able to implement it in one way where you say, okay, if I pass 1 argument, do this. If I pass 2 arguments, do that. If I pass 5 arguments, do this. So you can have multiple functionality for the single object. And you can do that in a very clean and simple way, right? So this is extremely easy to read. And if you know what this star is doing, then it's very explicit as well, right? There's no uncertainty about what's going on here. If you're not familiar with this thing, then it might be a bit strange. What's going on here? What does this mean? Right, especially if you're coming from C++, you might think it's a pointer or something. Okay, so is everybody clear on this particular example? Okay, great. So we're going to come back to that idea a little bit later, but first we're going to kind of get into the meat of Python, which is dictionaries, right? So I'm going to re-emphasize here today, like if you learn nothing else than how to handle dictionaries extremely well, then you probably can do anything in Python. And we'll see over the course of the day why that's the case. For now, just take my word for it, and then I'll convince you later. Okay, so let's start with a simple example. So any Ninja Turtles fans in the audience today? Oh, no? Oh. Tough crowd. Okay, so if you're not familiar, there are 4 Ninja Turtles. Each one of them has a different color bandana that they wear, and each one of them is named after a famous Italian painter, right? Now imagine, unlike me, you didn't grow up in the 80s loving Ninja Turtles, and you're having a hard time remembering which turtle goes with which color. Like, I can't keep it in my head. Well, okay, so let's say I'm going to write the code to help me remember stuff. Okay, so what I'm going to do is create 4 explicit objects. Each one is the name of one of the turtles, and the corresponding value I associate to that object will be the color, right? So I can assign each of the colors to each of the Ninja Turtles. And then if I need to look up one of them and say, oh, okay, so what was Leonardo's color? Oh, that's right, it was blue. So the problem with this, of course, is that I had to create 4 independent objects to store this information. Of course, there's only 4 turtles, so that's not a lot of information. But what if I wanted to do this for, stars in the Milky Way, right? So then it starts to become not very feasible way of handling this, right? So, we might think of maybe there's a better way or more compact way we can store this information. Okay, so we talked about lists and tuples already. So we're like, okay, well, one thing we know about lists is that we can create a single object that stores multiple values, right? So that by definition is pretty compact. So we could say, all right, let's create an object called turtles, and we could put all the 4 colors in there. And if we remember what the turtles' names are, and we remember the order in which we stored that information in the list, then we can recover the relevant information we need. But of course, the whole point we're writing this code was to remember things, right? So if I already knew that, then probably wouldn't need this code to begin with. So is there a better way to store all of this information I need, but also keep it compact? Well, the answer is yes. And that is using what's called a dictionary. So we looked at the syntax already for lists and tuples. So for lists, it was square brackets, and tuples is curved brackets. And for dictionaries, it's these what we call curly brackets. I don't know what the French is for that, but I'm sure it's something interesting. Right. So the structure of a dictionary is very simple. So you have comma separated values, the same as in a list or tuple, and those values correspond to 2 things. So one is a key, and the other is a value. So there's always a key value pair in a dictionary. So the key goes first, colon, and then value. Key, colon, value, key, colon, value, and so on. Okay? And that's the simplest way you can define a dictionary. So we could evaluate that. And then if we wanted to look up, well, we can start looking up some of the information that's stored in that dictionary. So we could print out the dictionary itself. We can print out the dictionary keys. We can print out the dictionary values, and we can print out what's called the dictionary items. So let's have a look at all those things. So if we print the dictionary itself, it actually prints the thing that we defined, right? So we get exactly what we typed in the first place is the evaluation of just printing the dictionary. If we print the keys, it gives us a list of the key values. If we print the values, we get a list of the values. And if we print the items, we get a list of tuples, and each tuple corresponds to a key value pair. Okay, so I will come back to this list of tuples idea a little bit later, so don't forget about this. But for the moment, you can see that basically, this basic information we've put into the dictionary, we can retrieve. We can retrieve just the keys, we can retrieve just the values, or we can retrieve both. Either way we want. It depends on the version of Python. So how do we index a dictionary? So in the case of tuples and lists, we had a integer value index. So we'd say, okay, I want the first element from this list. I would do square brackets 0. I want the second value from this list, square brackets 1, etc. That doesn't work in Python for dictionaries. So for a dictionary, we need to pass the key as the index that we're looking up, right? So not a positional index, but actually the key. And that's the whole point, right? So essentially what we'll say is, okay, we have my dictionary of turtles. I'm going to give it square brackets, and then I'm going to pass the name of the key that I want, and it will give me the corresponding value. So now I've kind of solved my Ninja Turtle problem, right? Because I have a dictionary that has all of their names and all of their colors. And essentially I can retrieve either piece of information extremely easily. And then I can index or do a lookup, which is called in this case, of any of their names and get the corresponding color extremely easily. And now the important thing is that, so again, we're only dealing with 4 pieces of information here, but dictionaries are highly optimized in Python. So the lookup is extremely fast. So the fact is that if I store a lot of information in these things, it's going to be a lot faster for me to do a lookup in a dictionary than it would be to index a long list. Right? And so this is a relevant piece of information. This is why basically the core of Python is built upon dictionaries. So it's important to know how they work. Okay, so up to here, is everybody happy? Good. Okay, so yeah, the important thing as well is that the lookup always goes key to value. and not value to key. Okay, so now what are some ways we can manipulate dictionaries? So dictionaries are mutable. So if we go all the way back to the very first things we talked about today, the difference between lists and tuples, right? So which one's mutable? Right, good. Somebody remembered stuff. Okay, so dictionaries are also mutable, right? Unlike tuples. So it works in two ways. So one is if I want to add a new element to my dictionary, I can do it via assignment. And that means is that if I take my existing dictionary, I create a new key. So this key does not exist already in the dictionary. And then I do an assignment to a value. It will then create a new entry in my dictionary with the corresponding key value pair. So you can see here, I've updated my existing dictionary and it has a new now key with the corresponding value. Right, so that's extremely useful because that means that we can very easily manipulate existing dictionaries in a fast and user-friendly way. We don't have to do some complicated manipulation or fancy, or you don't even need to remember some fancy function name or something like that. It's simply an assignment. Okay, so we can do the same thing to modify existing values for the keys. So now that we've added this key to the dictionary, we could say, now I want to change the value that's associated to this key. And that's also just an assignment. So I take an existing key, add a new value. And then when I print the dictionary, you can see that the value has updated in the dictionary. So again, makes the manipulation mutability of the dictionary extremely user-friendly. Okay. So if we try to look up a key that doesn't exist in the dictionary, we will get an error, right? So this is not an assignment because there's no equals. So without the equals, there's no assignment. It's simply a lookup. And when we do a lookup for a key that doesn't exist in the dictionary, we get a key error, right? Which is what you would expect. Okay, everybody happy? So that's like literally level 0 of dictionaries. If we're good from there, we can kind of step it up a teeny bit. All right, so in the previous section, we talked about unpacking, right? So we were like, okay, it's really handy to be able to take a tuple, for example, or a list and unpack it into individual objects. We can do the exact same thing with the dictionary, but the way it works is a little bit different, right? So firstly, if we have this dictionary, so we have keys A, B, C, and values 1, 2, 3, right? If I say unpack my dictionary into 3 values, I get the keys. Okay, so that's might not be immediately obvious. And the reason is that you can actually unpack the dictionary in multiple ways. And if you want to unpack the values, for example, you have to do that explicitly. So you would say, rather than unpack my dictionary, you'd say unpack my dictionary values. And if we go back up your notebooks a little bit, you'll notice that when we looked at the keys and values separately, we got a list of the keys, a list of the values, and a list of the items. So essentially all we're doing is unpacking a list. So the default list for a dictionary is always the key list. So when you say unpack my dictionary, what it's actually doing is unpack my dictionary dot keys, brackets. So if I want to unpack the values, I would tell it explicitly to unpack the values, and I can do so. So what would happen if I unpack the items? What would I get? Yeah, so what objects are those? So, no, almost. Yeah, exactly. It's a list of tuples, right? So the mydict.items is a list of tuples. So if I unpack the objects will be tuples. Everything okay? Right, so is everybody clear? So why we get tuples here? Okay, great. Okay. So now we can see that we can unpack dictionaries. And so we remember when we were talking about unpacking, one of the most useful ways to use unpacking was inside functions, right? So now let's say, well, maybe we can take advantage of the dictionary unpacking inside a function. And well, the spoiler is that you can, and it's an extremely cool feature. So in many, I guess probably all programming languages, you can set default values for arguments. So imagine I wrote this function. So very similar to some examples we had before. We have 3 arguments, A, B, C, and then we have a return. And we can notice that we're not even using the 3rd argument in this particular case, right? So meaning that, you know, we can have redundant arguments passed to the function. It doesn't hurt the functionality whatsoever. So we have 3 arguments, and we're going to call the function without passing any arguments. And the reason is because we're going to define default values for those arguments. So essentially, if this argument is not explicitly given, then I'm going to use the default value. And we can see, of course, it works, right? And so these are called what are called named arguments or keyword arguments in Python. Okay, so essentially, you have 2 types of arguments. You have positional arguments, so an argument that not named and it essentially matters the order in which it's given, or a keyword argument which is named and it can be given in any order as long as the correct name is provided. Okay, so yes, like I said, I can pass these arguments in any order I want. So instead of going ABC, I could call it CBA, and I could pass it to my function and it will work because it knows this is, okay, A is a named argument, so I'm looking for the value to A and I will give it to the appropriate variable. Clear so far? Okay, so now we can make use of a keyword expansion operator. So if we look at here, we can see it's a double asterisk, which is extremely similar to our splat operator before and does this very similar sort of thing. But it's instead of working on a list or a tuple, it's going to perform on a dictionary. So imagine we have a dictionary that has A, B, C. So we have 3 values with the corresponding the key and key value pairs. What I can do is, again, similar to what I had before, is rather than taking a list, explicitly indexing all of the elements in the function, I could just unpack it. So in the same way, if I have a dictionary with key value pairs that corresponds to the arguments I need from my function, I can unpack the dictionary directly into my function, and it works. Now this starts to become extremely useful, right? So now you could say, okay, I have a function that has 100 keyword arguments that I can give an immense amount of functionality to. I could essentially have something like a configuration file. I could read the configuration file as a dictionary and unpack that dictionary directly into my function, and it works. Right? So now I've got a lot of functionality with very little effort from Python. Okay, is that clear? Okay, so let's look at some other things that we can do with this. Okay, so imagine now I have a function, it's called subtract, and I'm going to give it some undefined number of positional arguments and some undefined number of keyword arguments, right? So effectively, these could be infinite because I have no limit on the number of positional or keyword arguments I can specify. It's expecting at least 2 positional arguments because I'm going to look up for argument 0 and argument 1. I want values for A and B, right? So I expect at least 2 positional arguments. By default, I'm going to calculate the difference between the first 2 arguments. Then I'm going to check to see if there are some keyword arguments. So what I'm going to do is say, if the key return abs is inside my keyword arguments and the value of that particular keyword argument is true, then I'm going to take the absolute value of that result. And then if the add value key is in my dictionary, I'm going to add the corresponding value to this key to my result, and then I will return the result. Right? So now I have a function with very simple, behavior, but I can add more complex behavior onto, which is completely optional. Right? So you can see here, I take, in the simplest case, I pass the 2 positional arguments, 1 and 2, and I get the result. If I say 1 and 2 and then return the absolute value is true, I get the absolute value. And if I say subtract 1 and 2, add 3, and then I can pass some dummy keyword arguments, you can see that I get 1 minus 2 plus 3. And this dummy argument has no impact on whatsoever because in no way am I using that keyword argument. I'm not looking for it, so it doesn't hurt anything. So essentially, you're free to pass unwanted or unused arguments to your function without any loss of functionality. So hopefully this will give you a taste of now, oh, this is starting to become extremely useful for what I can actually do. Any questions about this? Yeah. Okay, well, that's a good question. So, like I said, there's a difference between positional arguments and named arguments. So if you look carefully, you can see that 1 and 2 are just values, and return abs and add value have an assignment, right? So basically 1 and 2, there's no way to know what those would correspond to if it wasn't positional, right? Because essentially I have no idea if 1 is A or B or anything other than the fact that I expect A to be the first one and B to be the second one. So these are positional arguments, whereas return abs is named, right? So basically I haven't just passed true, I've passed return abs equals true. So I've named the argument. So that means that this can be passed in any order I want after the positional arguments, right? Because the positional arguments always have to come first. And then it knows that this is a keyword argument, and these are just args because they're positional. Good question. Any other questions? No? Okay. All right, so I think we're running a little bit late, but we can just kind of finish up with dictionaries and then maybe take a break. Okay, so now that you kind of got an idea of what a dictionary is, how to create a dictionary, how to manipulate a dictionary, and how it can be useful for designing functions. Now I just introduced a couple of tips and tricks that once you get a bit more used to using dictionaries might be helpful in your day-to-day life. So here's an example of like just building a dictionary from different types, different objects. So imagine somebody, a friend of yours, said, oh, I'm going to send you a list of my film collection. And for some reason, they chose to send you a Python file where they've created a bunch of tuples where you have the name of the film followed by the year that the film was released. Okay, it seems like a weird way to share this information, but you know, you have a weird friend, that's fine. So what you can do is say, well, okay, I've got all of these films. Well, I could make a list out of all of those films and print that, which will give me a list of tuples. Now, if you were thinking, you're like, hang on, list of tuples, that sounds familiar to me. I've been dealing with lists of tuples recently. I wonder what it was. It's like, oh yes, when I print out the items from a dictionary, it's a list of tuples. Well, amazingly enough, is if you just call the dict command, so the dictionary command on a list of tuples, it creates a dictionary. Voila. So now you can start to see, well, it actually becomes very easy to start building dictionaries out of non-dictionary objects, right? So you have some data that's been provided to you as lists or tuples and things like this. You can start concatenating those things and creating dictionaries out of them, which are then easier to manipulate and have faster lookup. All right, so you don't have to build your dictionary from scratch. You can actually take existing objects and make them into a dictionary. Okay. So you could also concatenate multiple dictionaries. So let's say, okay, now I got an extra dictionary of films and I want to have just the one dictionary because I don't want to have two separate dictionaries of films. So I want just a single one. Well, there's a very nice way using this unpacking keyword argument expansion operator. And what we do is we're going to define a new dictionary. So we have curly brackets and we're going to unpack the two existing dictionaries into our new dictionary. So it kind of makes sense. Essentially, we're just going to pour everything out into a new dictionary, and we get a new longer dictionary that's the concatenation of those two. So in a very simple one-line flow, no looping, no messy behavior, is simply unpack everything into a new object, and I have my nice new dictionary. Yep. No, because then you would have, well, one is what these curly brackets are expecting is a dictionary. So if you just put these items in there, it's not the proper dictionary definition. Because what you could create is a dictionary of dictionaries, but if you don't want a dictionary of dictionaries, you have to unpack your existing dictionaries into that new object. Okay. Okay, so then just a couple of like special commands that you can call. If you want to clear the existing contents of a dictionary, you can take the name of your dictionary, .clear, and that will empty the dictionary for you. Not something I use very often, but it's useful to know that that exists. You can also use these update, get, and pop functions to do similar sort of behavior. So the update will be adding a new item to your dictionary. Get would be looking up an item for your dictionary, and popping would be removing a single item from your dictionary. So we could take that dictionary that we just emptied and add in the film Back to the Future. We could then do a lookup on Back to the Future, and then we could then pop out Back to the Future to re-empty the dictionary. So important note. Just smaller. Is that there's a big difference between the get and the standard lookup. So you remember the standard lookup is we put it square brackets. And Valerie, are you online? Maybe you can mute your microphone. Okay, so we have we did the standard lookup was square brackets, and then we put in the name of the key, right? And we showed that if we put in a name that didn't exist already in our dictionary, we got an error. Does everybody remember this? It happened 5 minutes ago. Okay. So what the get procedure will do is instead of returning an error, it will return none. So if you have get for a key that doesn't exist in your dictionary, it won't raise an error, it will just return none. So this is important because you might want one behavior versus the other. So you might want to raise an error, like if this is not in my dictionary, I want it to break. In other cases, you must say, I don't know if this is going to be in my dictionary, I don't want it to break anything, so I will do a get operation so that I just get nothing if there's nothing in there, or I get the value I need. So this one, I think, out of all of these little tips is probably the most useful to remember. Okay. I think maybe we can break for coffee there. So is it upstairs?
Yes.
Okay.
Just a question like this: which language do you use every day? English.
That's pretty funny.
Any exotic language like Fortran or Java? Although ugly things like EDL.
MATLAB.
No, sorry.
That's pretty ugly.
We are just German, please. Don't hesitate to share your notes. I see some people take very interesting notes to put in the etherpad. Just to share with the
Is everyone happy with what we've gone over so far? Is there any questions from the first session? No? Okay, great. Okay, so everything that we talked about so far, I would like really put under the category of basic Python. So if you're really comfortable with that, you're on your way to being advanced in basic. So we're going to talk about some slightly more, like, let's say, high basic or early intermediate topics in Python now. So make sure that you raise your hand or ask questions or whatever. Don't be shy. Okay. So the first topic we're going to talk about in this session is list comprehension. So has anyone even heard this term before? Okay, so we're at 1, 2, 3. Okay, 4. All right. So not a lot of you. So okay, so this is something that I would say is now extremely Pythonic, right? So I mean, I'm not saying that this doesn't exist in any other language, but it's certainly not a common thing in most languages. And so this really just has to do with a different way of kind of handling loops and particularly loop objects. So I think, I hope everyone in the room has written a loop in some language at some point in their life, right? So this is pretty much standard in any programming language. At some point, you're going to have to iterate through elements, objects, operations, or something in the language that you're dealing with. Python is no different, but there are some different ways we can handle it in Python. So, all right, let's talk about like the simplest kind of basic thing. So this should be fairly self-evident to anybody who's written a loop before. So we're going to write a for loop with the for statement. We're going to have an iterate I, and we're going to loop through this particular tuple, in this case, 1, 2, 3, and then we want to print out the value of I. So, you know, as expected, we simply print out I equals 1, 2, 3, right? So this is more or less how loops work in almost every language, right? You have a for, you have some variable that you're going to use as your iterate, and then you have some object that you're iterating over, right? Whether it's an array or a set of conditions or something like that. Okay, so this everybody should be comfortable with that. So in Python, what we can do. So firstly, if we were to do this in a very un-Pythonic way, right? So here is an example of something you should never do, right? This is so we can compare to what you should do. Here's an example of what you should not do. So in a lot of, let's say, lower level languages, what you would do is you would have an array-like object with a defined size. So let's say I've defined a list of 3 elements. I haven't provided the values for those elements. I just want an empty list with a specific size. Right? Now, this is something you would do, for example, in C or something like that, where you explicitly want to allocate a certain amount of memory and then fill up those memory blocks. We don't want to do this in Python, but we can do this in Python. All right, so then we could say, okay, I'm going to loop over these elements. Then I'm going to take the I-1th element from this list and allocate the value of I to the list. Okay, it works. It's horrendous. Like, I hope that you never, ever, ever have to write something like this in your code, because you should never have to do anything like this in Python, because it's just not necessary. Okay, I mean, you know, you can do what you want to, but I genuinely, you know, advise you not to, because one, this is really hard to debug. It's really hard for a user to read. It's very hard to keep track of if you have multi-dimensional array elements and things like this. Keeping track of I, J, K, L, you know, all this stuff is a nightmare. It's just, you know, for the most part, it's not necessary. Now, if you think back to all the unpacking and packing things we've done, in fact, Python makes it very easy not to have to do these things. Okay, so let's say, how can we make this a little bit more Pythonic? Okay, so one thing we could do is, rather than specifying the size of the list, we could just create an empty list. Right? We don't need to allocate a certain amount of memory. Python really does all the memory management for you for the most part. We don't need to loop over a specific, you know, array thing. We can have a range like in many languages, and we can simply append values to the list that we're iterating through, right? So that's a little bit cleaner, right? So then there's no like indexing the ith blah blah element. We simply take an empty list and add as many things to the list as we want to, right? So we get the same information in a just cleaner, nicer way. But this isn't the most Pythonic way of doing this, right? Because if we're thinking about, okay, what do I want here, right? So what I want at the end is a list, right? So we can clearly see that my end object is a list of elements, okay? So the thing that Python will allow you to do is create a list element directly using what's called list comprehension. So list comprehension, so we're doing exactly the same thing we did in those 2 previous examples in one line. All right, so what are we doing? So we're defining our list object, right? So in the first example, we created a list object with a specified number of elements. The second one, we created an empty list. And in this case, we're creating the final list we want directly in the first assignment. Okay, so you can say, well, let's break this apart. So what have we got here? So firstly, we have square brackets. So we know that the object we're creating is a list. Right? By definition, square brackets means it's a list. Then what do we have inside the list? We actually have our for loop, right? So we have for I in range 4. So it's exactly the same as we had in the previous example, the exact same for loop. And then at the beginning, we have our iterate. So essentially it's saying, what do you want me to store in the list? I want you to store the value of I. And where do I get the value I? You get it from this for loop, right? And we can see that we do that in one go, right? So this is what list comprehension means in Python. Okay, so essentially what it means is that Python allows you to have more complex assignment operations inside the list for creating list objects specifically. So the reason why this is the most Pythonic way of doing this is because the end product we wanted was a list. And therefore, why have intermediate steps when we can just generate the list in one go? Now, in some cases, you might have a loop where you're not creating a list, you're doing some other sets of operations, in which case you should have a for loop, right? You might want to break, you might want to have something that checks for convergence or something, in which case you need the for loop to continue until at some point you want it to stop. In this case, that's not what we want. We want the end product, which is the list. We don't care how many things you need to iterate through. We don't care about that. We just want you to create the object that we need. So the best way to do it is through list comprehension. So is everybody more or less clear on what we just did here? Yep. So lambdas for actually producing a function, right? So that basically it's the shorthand for a def statement. This is the shorthand for a loop that creates a list. So were you here this morning for the lambda functions? Okay, okay. So it's a similar idea in the sense that the lambda function allows you a single line assignment where the object is a function. This is a single line assignment where the object is a list. Okay, so far clear, everybody? Okay, great. So here's a practical example. Okay, so now we're really going to start like challenging the way you think about things from whatever language you've come from and thinking about it in a Pythonic way. Okay, so imagine you have a problem is that you want to calculate the absolute magnitude of a set of stars, given the apparent magnitude and the distance in parsecs to the star, right? So some astronomer has given you 4 stars, their apparent magnitudes and their distance in parsecs. They've also kindly provided you with the equation you need to know to calculate the absolute magnitude. So they say, okay, could you now give me the list of absolute magnitude for these objects? Okay, so simple enough task. So one thing we can do is, well, we learned all about dictionaries earlier today. So maybe we can make use of those. So if we see in the previous thing, we had a table of objects. We have a name for the object and we have 2 values for each object, right? So it might be nice to compact all this information to make it easier to store. So one thing we can do is we can create a dictionary. So in this example, I've kind of a slightly complicated dictionary generation just to show you again how to combine different elements into creating a dictionary. So firstly, we have a dictionary explicitly defined for apparent magnitude and distance. We then put this in a tuple with the name of the star, right? So we do this for all of the stars. We put all of those stars into a list, and then we call the dict command on that list of tuples, which then in turn creates a dictionary, right? So then what we end up with is a dictionary with 4 keys, which are the names of the stars. And the values for each key is another dictionary, which is got the apparent magnitude and distance, which is, again, a key value pair. Okay, so we have a lot of information. And what we can then do is very nice lookup. So we can say, okay, my object is stars. I want to look up the star Rigel, and I want you to give me its apparent magnitude, right? So essentially, then we have a double lookup, right? So we do first lookup on the first dictionary, and then a second lookup on the sub-dictionary. Okay, so that's a nice, clean way to store this information, but I still need to calculate those absolute magnitudes. So let's do it the, let's say, less Pythonic way. So firstly, we're going to do, like we did in the previous example, we're going to define an empty list. We're going to iterate. My iterate is called star, so it could have been I, but let's be more explicit. So if we remember all the way back to the first thing this morning, the Zen of Python, one of the first things was explicit is better than implicit. So if your iterate is a star, you know that it's a star. If you know your object is a galaxy, if you know what it is, write it. You know that there's nothing stopping you in Python for being explicit. I doesn't mean anything, right? So unless it's a very generic thing or a sub loop that doesn't really matter what it's doing, why not be explicit with what the iterate is? So in my case, I have a set of stars and I want to iterate over those stars. So my iterate is just called star. So now when the person's dealing with this code, they know what the object is they're dealing with at any point in the code. Okay, so I don't want the keys because I don't care about the star names for this particular calculation. So I'm just going to calculate over the values. If you remember, the values in this particular case are also dictionaries. Then I can write in my equation. So I have star apparent magnitude minus 5 times the log base 10 of the distance plus 5. And then I'm just going to round that to the first two decimal places. Okay. And then I'm going to append that value that I calculated into my list. Okay. In which case I can calculate all the absolute magnitudes for those 4 stars. So nothing particularly wrong with this at first glance. Does anyone want to tell me what's bad in this particular example? Yeah, feel free. Just. Not really bad, but the fact that we call the star. Yeah. The star is actually yeah, that doesn't matter, right? So what I'm yeah. Sorry. Yeah, I mean, so it's less obvious, but I think the thing for me, if I saw this example in somebody's code, is like, why are you doing the calculation inside the loop? Right? This is completely unreusable code. Because if I have to recalculate this, I have to create a new loop and redefine the same equation to get the values. This is really bad, right? Because essentially this is an explicit calculation, right? This formula doesn't change depending on the set of data I'm dealing with, right? This is something that should be defined as a function where I can control it, I can test it, and so on, right? The other thing is that my end product is a list. Why would I go through all of these steps when I know that Python can create list objects directly and have this messy thing of creating an empty list and then filling the list when I could simply do that in one line? So let's have a look at the more Pythonic way of doing it. So firstly, we can define a function for calculating our absolute magnitude. So now we have some abstraction, right? So we're going to talk a bit about this in the afternoon, but a bit of abstraction. So firstly, like the absolute magnitude has nothing to do with that loop, right? The absolute magnitude is a calculation that I should be really abstracted from the process I'm doing. So define a function that calculates absolute magnitude. So what does it need? It needs apparent magnitude and distance, and then I can return the same calculation I had before. Now, of course, in development code, you probably want a lot of documentation and all sorts of things, but for this case, we'll just keep it simple. And then something missing there. Yeah. I think there's hidden cell or something. Hang on a second. Yeah, I don't know why it's not here. Okay, so let's just go down here. Okay. Okay, so we want a line like this. So basically here what we have is our list comprehension. So again, what do we want? We want a list. So we're defining a list. Okay, what are we iterating over? We're iterating over the values in my dictionary stars. And then what do I want? Well, I want the absolute value, absolute magnitude. So I take my absolute magnitude function and I can stick it directly into my list comprehension. Right? So essentially, now I have one line implementation and a very simple and concise function, right? So you can see here, I've done exactly the same thing as in the previous example, but this is now reusable because I could create as many of these objects as I want using the same function. And it's clean. This is very nice and tidy, simple, and explicit. Any questions? Okay, so this is, okay, it'll take a while to get used to if you've never used list comprehension before. But the idea being is that you can make your coding life in Python a lot easier by getting used to these sort of frameworks, right? Because one is you can save a lot of space for very simple things, right? Again, if I know that I want a list object at the end, and I know that I have a specific amount of calculations to do or something like that, it's going to be a given size, why not just generate it directly? Having all of these I minus 1 plus j blah 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 things is a mess, and nobody's going to be able to follow it or debug it. This would be extremely easy to debug, right? So basically, I can debug this function independently from the actual list comprehension, and the list comprehension is so simple that there's not much to debug, right? You're either getting the object you want or not. Okay, so that's just one simple example. I'm going to show you another one, and again, the idea here is thinking to code more like a Pythonic person rather than a generic coding language person. Okay, so here's another example on the same sort of lines, right? So again, now this time, imagine we want to calculate redshift given observed versus emitted wavelength, right? So we have a list of wavelengths, and so we can do something similar. So we could have a definition of a function that does our redshifts, and we can have our list comprehension thing. But imagine this case, somebody didn't give us a dictionary. They gave us two lists. So they give us a list of the emitted wavelengths and a list of the corresponding observed wavelengths, right? So we could create a dictionary from these objects if we wanted to, but we might not need to. Like, we don't need to have an extra intermediate step onto this processing, because what we could do is simply stick both of them into our list comprehension expression. So we could say, okay, what do I want? All right, create a list. Provide inside the list the value of redshift for a given value of the emitted and observed wavelength. Iterate over both emitted and observed wavelength from this object. All right, so we're using this special zip function, and I'm going to get you to guess what that's doing in just a second, and you can see that it works. Right, so can anyone tell me what zip is doing in this example? Right, so it's a thing that we've covered a few times today. And if you think back, the previous example, we were using a dictionary. If you think back about how we could produce dictionaries, what is a dictionary made up of? Any guesses?
In order, the first,
oh yeah, so what is the name of the objects that it's creating? Exactly. It creates a list of tuples, right? So if you remember, when we produced our dictionary, we could look at the items, which is a list of tuples. We could take a list of tuples, run the dict command on that, and produce a dictionary. So in principle, when we were looking at the previous example, we were iterating over the dictionary values, right? So, it's a very similar idea. So basically, oops, let me go back into, as you see here, that zip on my emitted and observed will produce a basically iterator expression, which we'll cover in a second. And then if we convert that into a list, you can see that we end up with a list of tuples. Okay, so essentially what's happening in that previous example is that we are looking for E and O for each pair of tuples. So basically we're going to take E and O for first tuple, then E and O for the second tuple, then E and O for the third tuple. Right? And that's exactly the same sort of thing that was happening before with the dictionary. All right, so this basically allows us to iterate over two lists simultaneously to get the corresponding elements always at the same time, right? So now, again, this is much cleaner than having to say for I equals blah, iterate over this list I, that list I, and then put these two things into a function and so on. I can do that all in one line, very nice, neat and clean. List comprehension. So is everybody understood? Yeah, yeah. Yeah.
This means that it would work if I have the dictionary of
Yes.
of the two.
Yes.
As an argument, the dictionary.
Exactly. Okay. So, the couple of examples that we looked at so far, we're just doing a very basic loop, right? We're saying, okay, here's a list, here's a dictionary, here's some tuples, whatever. Iterate over those things and stick them into my function. But often when we're, using, lists for statements in real life, is we have some conditions. We're like, if this object is such, then do this, and so on. Well, we can actually do that inside list comprehension as well. So imagine now we have a list of names, all right? And we want a very complicated subset of these names. So we want to take every name in this list that has the letter E and for which the first letter is lower than K in the alphabet, right? So you can imagine if you were going to write this in some language, it might require a large number of conditions and everything to get very, simple output at the end. In Python, that's one line, right? So what are we doing? We're going to take the name for name in name. So what that means is the iterate is just the output of the object in the list. So loop over all the names in the list names, give me the name at the end, but only if there's an E inside the name and if the first letter of the name is less than K. Fortunately, Python's pretty smart and can actually do less than greater than with characters as well as numbers. And you can see it works. So you can still see that you can actually do like some pretty complicated things with very small amount of code in Python, if you understand the logic in list comprehension. Because again, what did I want at the end of this? Well, I wanted a sublist from my original list. So again, why create an empty list and then take things from that list and stick them in there when I can simply produce a list in the same process in one line? Okay, so here's another example. So I'm guessing there's no Thundercats fans, given that the Ninja Turtles weren't very well received. Okay, so this case, we have a slightly different object, right? So previously what we've been looking at is a list. This case, we have a nested set of lists, right? So basically we have a list of lists and each one of the sublists is of different size. So we can see we have first list has 4 elements, the second list has 2 elements, and then the last 2 lists have a single element. So now imagine someone says, okay, I want just a single flat list, no nesting whatsoever, and I only want to keep Thundercats. So for anybody who's an expert would know that Mumra is the bad guy, he's not Thundercat, so we need to remove him from the list. So again, rather than making a whole messy amount of code, I can do this in one line. So what am I going to do? All right, first I'm going to iterate over the main list. So I'm going to make an iterate called groups, which is going to be my sublist inside the bigger list cats. Then I'm going to do another loop for each element in each subgroup called cat. And then I'm going to check to see if cat is not equal to Mumra and give back cat. And I end up with a nice flattened list without that one object. Okay? Nice, simple, and clean. No indexing, no mess. Right, so the tricky thing is, of course, just getting used to the order in which you need to call the lists and so on. But again, if you sit down and play with it, it just takes a little bit of practice. You create some objects you want to play with, see if you can index them in the right way, and you'll soon get the hang of it really quickly. But you'll also be able to write very nice, clean Pythonic code. So any questions about this? All right, wonderful. Okay, so now we're really going to step it up a bit. So I hope you've all been paying attention. So we're going to talk about iterators and generators. So this is really now when we're starting to think about, okay, I've now really comfortable with dictionaries, really comfortable with list comprehension, really comfortable with Python objects and functions and so on. But I want to start making my code a bit more optimized. When I'm producing lists and tuples and dictionaries, they all take up memory, right? So if I have a huge list, it takes up a lot of memory. But sometimes you don't need to use that memory if you don't need all of that information at once. right? So imagine, you want to iterate over some objects and you just need them one at a time. There's no point in storing the whole thing in memory and then just looking at each object one at a time, when you could just keep only the thing you're using in memory at the moment you need it. So that's kind of what the whole point of iterators and generators are. It's going to take just a little bit of playing around to get used to this, but let me just show you first how you would create an iterator. So here we have a list. We know how to define a list: square brackets, comma separated values, no problem. We can then call the iter function on this list, which will produce an iterator. Now, if we print the iterator, all it's going to do is tell us that it's an iterator, right? So it's really not giving us much information about what that object is. All we know is what type of object it is. So we can do the same thing with tuples. We could take an existing tuple, again, 4 values, and create an iter object from that. And again, it's just going to tell us it's an iterator. It's going to tell us it's a tuple iterator, but it's still just telling us that it's an iterator. So now, how would I extract the information I need from that iterator? Well, before we do that, just a quick, well, no, I guess I kind of spoiled it there, but it's just if you wanted to convert back from an iterator into a list or a tuple, you could take an iter object and call the list function on that object to convert back, right? So essentially, if I had a tuple, I converted it into an iterator, I could then convert the iterator into a list and retrieve a list, right? So this is just basically to show that you can change back and forth between these objects very easily in Python. But let's go back to how we get objects out of my iterator. Okay, so now I created an iterator. If I print the iterator, it tells me it's an iterator. Can I index the iterator? So can I get the first element from my iterator? The answer is no, right? It's not an indexable object, right? And the reason for that is, in order for something to be indexable, it has to be stored in memory, right? So if we have a list of 10 elements, it's stored in memory, and then I can index the element I want from that list and retrieve it, right? And the reason for that is, in order for me to be able to index it, I need to know how many elements are in the object. And in order to know how many elements are in the object, it has to be stored in memory. Okay? So basically, once I convert it into an iterator, I no longer know how many elements are in the object. But that's fine in certain circumstances. So there's a special function called next, which I can call on my iterator. So if I call next on my iterator, I get 1. If I call next on my iterator again, I get 2. If I call next on my iterator again, I get 3. And so forth, until I get to the end of the iterator. So what you're seeing here is, rather than giving me all of the elements in memory stored at once that I can index, it's giving me 1 element at a time every time I call next on that object, right? Now, why is that useful? So imagine I had to do a loop over 1,000 elements. If I had a loop, if I said loop over this list of 1,000 elements, I have storing a list of 1,000 elements in memory just to do a loop, which is a real waste of memory. So what I could do is, instead, I could create an iterator object that has been created from 1,000 elements and just call next every time I need to get something from it. And then I'm only storing the one value, the iterate value that I need at the time I need it, right? And then it will stop when it gets to the end of the iterator. Is that clear? Cool. Okay. So what are some cool things that we can do with iterators? So if we take a list and we create an iterator from that list, I can run sum on the list and the iterator, right? So I don't actually have to convert it into a list in order to sum the elements from the list. Python can automatically unpack the iterator and get you the sum in one go, right? So we can see it's equivalent. So in fact, in some cases that, the important thing to note is, of course, that this one is using a lot of memory and this one is using very little memory. So if all I wanted was the sum at the end, there's no point in creating a list. I could just create an iterator. But beware, because if you call the sum again, the list will return the correct value, but the iterator has been already unpacked in the first time we called sum and now is empty. So calling sum on the object again gives us nothing. So this is kind of like a one-shot and you're done situation with iterators, right? Once you unpack your iterator, it's unpacked, and you either have to repack your iterator or you leave it. So you have to find the right situation for when an iterator is appropriate in your code. So for example, for loops are a perfect example, because once you're done looping, you're done, right? That's the end of your thing. So that's an excellent opportunity. So nicely, most of the things, commands like range and so on in Python automatically create iterator-like objects. So by default, when you say range 5, it's not creating a list of 5 elements, it's creating an iterator of 5 elements. And basically, so when you loop over a range 5, you're looping through the iterator, and you're only using the memory that you actually need. Okay, so another example is there are many built-in functions that behave like iterators. So one of them was zip. So we looked at zip a bit earlier. We realized, okay, if we had a couple of lists, we could create a basically list of tuples from those lists. But in fact, zip itself doesn't create a list. Zip creates a zip object, which is very similar to an iterator object. So if I take 2 lists, 1, 2, 3, 4, right? Running zip on this should create a tuple of 1, 3, 2, 4 pairs, but as a zip object. So in fact, calling next on my zip object will work. You can see here, so we got the 1, 3, 2, 4, and then of course there's no third tuple pair, so it stops. And therefore, when I call list on zip, what I'm doing is actually unpacking the whole zip iterator object into a list. Is that clear? Okay, so we're gonna step it up even another level. So any questions on the iterators so far? No? Okay. So generators. Okay, so in the iterators, we were looking at really, okay, we could take a list, we could turn it into an iterator, and we know that there are certain Python objects that behave like iterators already, like zip and range. But what if I wanted something a bit more customized to my specific case? How could I produce something that behaves like an iterator, but it has a bit more complicated behavior? So this is where generators come in. So, okay, so here's an example. Let's imagine we want to have a function that calculates the square of an input value, or a set of values rather. So we have a set of values. Inside our function, we're just running a list comprehension. We're saying, okay, take each value in my list of values and return the square into a list. And then I could provide a list to that function and get the corresponding squared values. Okay, nice and simple, nothing particularly complicated. So of course, this function is taking a list which is stored in memory and providing a list which is stored in memory as output. Okay, so what if I don't want all of the squares? I just want each square as I call it when I need it. So then I can use this fancy yield statement instead of return. So return is expecting a value. Yield is telling the function that you've just defined that it's no longer a function, it's a generator. And what it should do is generate the result when it's called, rather than producing the result directly into memory. So let's look at, so it's a similar problem, not exactly the same problem. So we're going to provide, again, a list of values to the function. We're going to loop through the values in that list, and then we're going to yield the square of that value when called, right? So basically what I can do is take my function, provide this list to it, and I create a generator object. So my generator is the assignment of this function to some values. And then by calling next on my gen, you can see that I get the squares one at a time. So only when I need them. And then basically, I'm only storing one value in memory at any given moment. Okay, so the thing is, you're getting exactly the same kind of iterator behavior, but I get to control what the iterator produces. And that's why it's called a generator. Yes, of course. Sure. Yeah. Yeah. Absolutely, right. So that's the thing. But that's the thing is that, you know, when you have stuff stored in memory, you have much more flexibility is what you can do with it. But of course, you have to decide, do I need this stored in memory or not? And this is where the optimization comes into place, right? Because if you don't need it stored in memory, then you're wasting memory. And if you can avoid wasting memory, then you have more memory for other more important tasks, right? So, this is just an example of how the generators work. We'll have an example of more practical application of this a bit later. Okay, so another thing is that generators can have multiple yield statements, right? So a function can only have one actual return statement. You can have ifs that have different options for different returns, but in the end, the function will only ever use one of the return statements. Whereas a generator can actually yield multiple yield statements in the same generator. So this is just an example. Let's say we have a function that has no arguments whatsoever. While true is more or less like an infinite loop. And we're going to say yield this, and then the second yield will yield a different statement, third yield a different statement, and fourth yield a different statement, right? So what do I do? Okay, so I create a generator. So assign to an object an instance of my generator, and then run next on that generator object. And you can see we cyclically loop through the yield statements, right? So, I mean, let's say in astrophysics context, I can't think of many times where you're going to use multiple yield statements. But if you were developing a user end for somebody, where you're like, okay, if you click the box once, print this message. If somebody clicks it again, there's a different message. If someone clicks it the third time, you're like, okay, stop clicking the box. That's enough. So you could see, think about, more kind of interface sort of applications for multiple yield statements on a single function. So again, you get complex functionality from very little code. Okay. Okay, so finally, we talked about list comprehension. So, yeah.
We saw that so you can create a lambda function in place of the return.
No, yeah. No, so it's not to rephrase the return. The lambda replaces the def. Yeah, so when you define the function, the def at the top, the lambda is replacing that.
Yeah, okay, but you also don't write the return.
No, you don't write return because it's
yeah.
It's yeah.
Then you do that the same lambda function but with the generator.
No.
With the yield.
No, because it's implicitly return. Yes. So what you can do is create a generator expression. So similarly to list comprehension, we can produce generator expressions inside curve brackets. So when we had a square bracket, we were producing a list comprehension. If we do the same sort of behavior inside curved brackets rather than square brackets, instead of creating a list, we're creating a generator. So for example, we had, you could imagine earlier that we have a for loop. Okay, so we have range 1 to 6. We want the values from 1 to 6, and we want the square value. So if this was a list comprehension, that would be square brackets, and at the end we'd end up with a list object that had all of the outputs. With the curved bracket, the inside stays the same. All of the comprehension logic stays the same, but the object that you produce is not a list; it's a generator. So now, by calling next on that, we get the outputs. So now we have an even easier way to produce generators than with defining a function with a yield statement. We can have a single line. So now you can start to see, okay, inside my code, I want you to loop over some complex list comprehension. Well, if you're only looping over the list comprehension or something like that, then you could change that to a generator object and then only extract into memory what you need at the time you're using it. Okay, so now we're starting to get into slightly more intermediate territory here. So if you really wrap your heads around this, you're in pretty good shape. Any questions? Yeah. Yes, okay, so that's a good question. So, so there is no tuple comprehension. So in fact, if you wanted to use list comprehension and produce a tuple, what you would have to do is a list comprehension, create a list object, and then run tuple around the tuple function around the list object to create your tuple. Because this is just a kind of, I guess, limitation of the number of symbols that you can use in Python. They chose this symbol for generator expressions. So in fact, if you think you're generating a tuple from this, you'd be wrong. And that's an important thing to know. So it's a good question. So if you have a comprehension statement inside curved brackets, it's a generator. If it's just values, then it's a tuple. So you have to be careful about that. Okay. Any other questions on generator expressions?
That would be another loop. Or...
Yeah, you could loop. You could write a loop that goes for next. You know, but I mean. That's essentially like what I was saying, that you would have a loop or a while statement or something that would extract values from your comprehension object when you need it. But it depends on how it's used, like in the context. Okay, so I have another just quick example, is that you can, of course, like I said, you know the way you can run sum and various functions like this on iterator objects rather than just a list. It works on generator objects as well. So essentially, I could say, okay, I want values cubed in the range from 0 to 9, and I want the sum of all of them, right? So rather than creating a generator object or a list comprehension and extracting all the values and then summing them, I can do it all in one line. And this, importantly, has used less memory, because in this process, I have never created a list into memory. I've extracted all the values into the sum as they were needed. So this is more efficient implementation. So these are the kind of little things that you can start to notice in your code. Like I have a loop kind of like that. If I just replace the square brackets with round brackets, then suddenly I'm using less memory in my code overall. So I can start, yeah. Yes. I think there's not a huge difference. I guess it depends on what you're doing, right? So if it's just like a sum or something like that, I think it's probably about the same. But you know, if you're looking for like specific values and you have some complicated evaluation, then it might be a bit slower. It depends on the actual code. It'd be hard for me to think of very generic, all cases included would be exactly the same. I would say for the most part, the computation time should be the same, but you're saving memory. Any other question? Yeah.
So, is it possible to have strings as elements?
Yeah.
So, can you remind me the main difference of using a multiple yes statement?
Mm-hmm.
For example, the one
yeah.
Or like an iterator with the same strings using the next.
So I don't think I understand the question.
So,
So okay, let's go back.
Yeah.
So you were talking about the multiple yield statements.
Yes.
Was it this one here? This one, sorry.
Yeah, exactly. So, so in this case, you made the example, for example, doing a click and getting the first
Yeah.
and so on.
Yeah.
And it's very different. So this is very different from having an iterator whose elements are strings.
Okay, so the thing is that right, so basically iterators, like you would generate, like, so let's say you had a list of strings and you created an iterator out of that. It would be like creating a generator, but with one yield expression, right? So basically it would only yield the value as you want it, right? So this thing is, this could yield different things each time you call it, right? So you could have a function that said, okay, the first time you call it, I want you to give me the square of a value, and the second time you call, give me the cube of a value, and then the third time you call, give me, you know, the division by 5 of this value, right? So you could have it doing different calculations every time it's called. So like I said, I can't think of many practical applications in which you would want multiple yield statements in your code, but it's useful to know that you can, right? Because you never know, you might think of a very clever way of solving one of your problems by having an extra yield statement or something like that. Honestly, I don't think I've ever written a piece of code that had multiple yield statements, but you know, knowing that it's there is helpful, because then you understand how it works, right? Because if you did use somebody else's code and you were saying, oh, this is very strange, every time I call this generator, it gives me something different, you could go back and look inside their code and say, oh, they had multiple yield statements. Now I understand, first time it called this one, and the second time it called this one, and so on. Okay. Okay. Right, so that's it for this notebook. So I have got some exercises that I've included. So the first one is basically just like playing around with dictionary manipulation. So like I said, probably if you learn nothing else from today, just learning how to manipulate dictionaries will really put you, you know, a long way towards being a good Python developer. So this is just a simple, you know, exercise to practice with that. Then I have one on list comprehension, just like similar to the examples we looked at for calculating the absolute magnitude and redshift. Try to do it yourself using a function and so on, seeing if you can get the correct results. Then an unpacking example, just saying, okay, if you can unpack something using list comprehension. And then finally, a really good example of when you would want a generator. All right, so if you want a function that calculates the Fibonacci sequence, which is infinite, you really don't want something that produces a list, right? Because you can't have a list of every number ever, right? So you'd rather have something that produces the next value in the sequence when you need it, right? So that's exactly what your exercise will be, to write a generator that produces a Fibonacci sequence. So exercise 3 was to use list comprehension to flatten a nested list. Okay, so we saw a couple of examples kind of similar to this throughout the notebook. So the main trick was just figuring out kind of the hierarchy that you need in the list comprehension to make this work. All right, so I'll just show you the solution to this. Basically, right, so we have here defined the nested list, or we have basically a list of lists which also contain lists. So there's a lot of depth to this particular one. So the solution was basically to think, okay, I need to loop first through the first list, right? So basically I need to do a loop of sublists in my list. Then since each one of those lists contained the list, I need to do another loop for the sublists in sublists in the sublist. And then I want to extract the values from the sublists. So then for value in sublist and to return the value, right? So, and then at the end, you'll get a completely flattened list. So was anyone able to do this morning? Nice. Nice. Okay. Well, a couple. Right. So it was just like, again, not a particularly useful example, but it's just to kind of help you understand the hierarchy of how the list comprehension does the unpacking, right? So that you know, it's going to need to start the for loops in the right order and so on. Okay. Any questions about this exercise? No? Great. All right, so then the last and definitely the hardest exercise from this morning was to use a generator to write a function that could produce a Fibonacci sequence infinitely, right? So just a quick show of hands, was anyone able to get a Fibonacci sequence? Oh, okay, great, we got one, that's pretty good. Of course, there are many different ways to do this. So I'll just show you one possible solution to this problem using a generator. Of course, you might have done something a bit different, but as long as you got the right output, it should be fine. So here's my solution, right? So basically, I define a function called fib with no arguments. I set some initial values. So I have a parameter called previous value and another one called new value, right? So I start initializing with values 0 and 1. I set an infinite while loop, and then I use a generator to yield the previous value on each call to the generator. Then I have an update step where I simultaneously update the previous value and new value to previous value to new value and new value to new value plus previous value, right? So that I have an addition, right? So then by initializing a generator object from my generator function, I can call next on that infinitely and get the Fibonacci numbers. And you can see I can add another one and another one and keep going as long as I like. So main point here was really just, this is extremely simple implementation, right? You can see there's only a few lines of code. But the main trick was just to figure out how to use a generator with the yield statement to be able to do this infinitely without using up any memory effectively. So is this solution clear for everyone? Is there anything weird about this? So there's something new in this solution that I haven't introduced in the notebook. So I don't know if anyone's picked up on it. Well, so basically I have here in this line a simultaneous assignment. We haven't talked about simultaneous assignments. So, so the thing is that this isn't doing assign this value, then assign this value. This is assigning both values simultaneously to new values, right? So it's basically using the same principles as unpacking that we showed earlier on when we were talking about unpacking tuples. Right? So the point to note is that when you're doing this unpacking, you're not assigning one object at a time, you're assigning all of them simultaneously. Okay? Any questions about exercises before we move on? Okay. A deafening silence will conclude that section. Okay. So I will upload all of these solutions to the repository after the sessions are finished, so that you can go back through and relook at the exercises in your own time. Feel free to try to work it out yourself. Maybe, you know, taking inspiration from what you've seen, but maybe not remembering exactly what it was. Try to do it yourself.